continue. We continue with the next presentation that will be given by Kuan Chen, who is the technical support manager at JA Solar, and he will present about what JA learned from using 182 millimeter modules for utility scale applications. Kuan Chen, Michael, the floor is yours.
I'll share. Okay, good afternoon and good evening. I'll share my screen. Hi, everyone. In today's presentation, I will talk about the JA Solar DeepBlue 3 182 millimeter wafer product and how it could be a premium solution for the best LCOE. In this presentation, it will begin with the design idea of our DeepBlue 3 product, and then the technical highlights of this product will be introduced. Finally, a brief value analysis of the DeepBlue 3 module will be presented. Okay, now let's go to the first part, the design idea of DeepBlue 3. To start with, I will have a brief introduction of the development roadmap of module power. We could see a trend of advanced module power from the graph, from which we could see that the leading module power has sharply increased from 290 watts in 2009 to more than 500 watts on the second half of 2020. There are several stages for the module power increasing. You could see that the leading module power is just about 290 watts in 2009. During this period until 2012, the increments of power are mainly optimized by raw material. After then, from 2012 to 2014, enlarging the sheet resistance and busbar upgrade becomes a common method to improve the performance. However, without much improvement. The revolution begins since 2014 with the application of the PERC technology, especially PERC with selective emitter following with multi-busbar and half-cell optimization. You could see that the leading module power is increasing rapidly from 330 watts in 2014 to 410 in 2019. And after the second half of 2019, increasing the wafer size becomes a common method to improve the module power output. And it does have a significant positive effect on the leading module power, as you could see that the leading power is changing from 410 to 500 in just 1 year from the second half of 2019. The leading module power nowadays could even reach to 550 watts and 670 watts, depending on their wafer sizes and models. Okay, and here are the methods used of increasing the solar module power. The first type of method, which is also the most effective way, is to increase the efficiency of the solar cell. The efficiency of the monocrystalline cells increased from 17% in 2009 to 23% in 2020. And the mass implementation of PERC technology boosts the cell efficiency. The development of advanced cell technology also benefits for the higher cell efficiency. Another type of method is to use advanced module encapsulation, including anti-reflection coating glass, which is to increase the light trapping, thicker and softer ribbon, which is to reduce the resistivity loss and pressures on the cell, as well as the high transmittance EVA, which could pass through more incident light, as well as the half-cut cells with multi-busbar fingers, etc. And the method commonly used in recent years is to enlarge the wafer sizing. As you could see, that the wafer size is increasing from 122 millimeter to 182 or 210 millimeters nowadays. And we ever evaluate the balance of system costs for the module using different size of wafer. The graph shows the trend of variable BOS cost as the wafer size and module size increase. It could be apparently seen that under the same cell efficiency, large module with higher output could reduce the BOS cost significantly. However, things will change as the module size becomes too large. As you could see that from the graph, after the module size becomes too big, there will be much less reduction for the BOS cost because the manufacturer has to pay more for the materials and components that could fit the large module. Large module could also bring more potential risks that will be introduced later. However, the things will be different if keeping increasing the module efficiency. The size of the module are large enough and almost hit a bottleneck in the whole industry. And the module efficiency may not go further just relying on increasing the wafer sizing. For the relations of how the solar module efficiency affects the BOS cost, it can be apparently seen from the graph that higher module efficiency could significantly reduce the BOS cost, since the size of the module has reached its limit. Increasing the module efficiency could be the top priority. Therefore, we should put more concentration on how to improve the efficiency using new technology. The data also shown that on these two pages are based on the analysis of a specific project. And it could be just as a reference. If you want to do accurate evaluation, case-by-case studies should be taken. And some may think that the higher the module, the better it will. Is that true? The answer is no. Firstly, if the module size becomes so big, it will also make the design and the production of the module much more difficult. Also, it will reduce the mechanical and electrical property of the module. Secondly, there could be potential risks for the large module if not properly assessed. The first risk could be the challenge for the solar module mechanical load. The mechanical property could be decreased significantly as the module becomes larger. And there are many examples that shows the reality, as you could see from the picture. The module are away from the rack under some extreme condition. Second, the large module will make the transportation and installation more difficult, and more labors have to be used for the installation using the large module, which will increase the cost. Moreover, there is also a challenge for the design of mounting system, especially in high wind region. As you could see, is that the larger module can easier to deform, and more requirement for the design of module as well as the mounting system has to be considered. Therefore, we have to seriously assess the risks when using extra large modules. And here is the comparison between the high voltage, low current module and low voltage, high current module. According to the equation, power equals to voltage times current. It could be known that higher power means higher voltage or current. There is an advantage for the low voltage. That is, the low voltage could increase the number of modules in a string and hence decrease the system cost. However, the risk of large module on a system and module itself cannot be ignored, and we have to take it very seriously. Higher currents would also bring more operation loss that will be introduced in the next page. In this page, it is the operation loss comparison between the G12 and the M10 wafer module. And the data used are just as a reference. It could be seen that more bus bars are needed to reduce the resistivity loss and increase the module power. After comprehensive analysis and optimization, we use 11 bus bar cells for our M10 modules. It could be also seen that the resistivity loss for the 210 module is generally higher than the 182 module. Therefore, there will be more cell-to module loss. Moreover, more bus bars are needed for 210 module to increase the power and reduce the resistivity loss, which increase the module production cost. The larger resistivity loss also bring higher temperature, which will decrease the performance of PV module. Moreover, there will be more potential risks for the burning out of the connectors and junction box diodes under the high working temperatures and large currents. And we did a comparison between the high current module and our DeepBlue 182 module. The high current module have much larger daily resistance loss under the same irradiance at the same time. Higher resistance loss also means higher working temperatures of module. DeepBlue 182 module produce more electricity than those of high current modules. So it will lead the lower levelize the cost of energy, which will also be beneficial for the end users or customer. After talking a lot about the idea of the 182 module, you may ask why the M10 wafer module is preferred. That is because the dimension and the electrical property is more easily fitted for the whole industry chain, including installation, transportation, and solar system configuration. The dimension of 20 to 78 millimeter long and 1134 millimeter width panel will be available in the beginning of the next year. With the module dimension and installation holes become standardized in the industry, it will be bringing more benefits for the customer to choose the product and design the PV system. We have also done a site survey cooperated with TÜV Nord in National PV Experimental Center in Yinchuan Province, located in the northwest part of China. It shows the performance of different types of module. We could see from the graph that 182 module can produce more power than large current module, especially during the summer period. The average relative power gain could be more than 1.9% from February to September. It does also have significant effect on the total electricity yield for the utility scale project. And it can be seen that the module temperature of 182 module are generally lower than the larger current module in daily operation. It could be seen from the graph that the maximum temperature gap between the high current module and 182 module could be up to 4 to 5 degrees Celsius. And the average temperature for 182 module is 1.9 degrees Celsius lower than a high current module. And our DeepBlue 3 product also awarded with high all-quality matters in energy field simulation for monofacial monocrystalline groups. To do this simulation, 5 modules are randomly selected from the 1,000 pieces mass production modules. The electrical performance under the different irradiance, temperature, and light incident angle are tested. Based on this data, the PAN file parameter of modules are determined and will be used for the simulation. And the simulation used the geographical and meteorological data of 5 typical areas in China, Germany, Saudi Arabia, Brazil, and India. And the modules are ranked based on the data gathered from the tests and the power of the module. Also, our product was awarded with TÜV Nord Outdoor Yield Performance Awards. It shows an excellent power yield performance. Okay, and now I will move on to the part 2, technical highlights of our product. Firstly, I will talk about the key configuration of our DeepBlue 3 module. All the modules are using M10 wafers and half-cut cell technology. And there are 3 types of modules, which are 54 cell model, 72 cell models, and 78 cell model. The highlights of this product could be the wafer size upgrade and the application of the 2nd generation PERC technology. Moreover, the technology used are compatible with our previous production lines, so the facilities workmanship are all experienced operated and materials used are all with comprehensive assessment. And this helps the product yield rate maintain in a high level to ensure the high quality of our product and to be cost effective to the customer. And here are the solutions for us to reach the best levelized cost of energy. It includes the Percium cell technology with high sheet resistance and high density grade, wafer size upgrade, gallium nitride wafer, and the usage of 11 busbar and half-cut cell technology. And now, I will have a brief introduction of the key technology of our Percium cell. The cell technology we have been using recently is upgraded generation of the PERC technology. As we know, the basic principles of PERC cell is using the dielectric passivation layer, which could increase the minority carrier lifetime. And also, we need to open slots before screen printing process in the backside, which is to increase the conductivity of the back contact. However, there are limits for the cell structure, that the sheet resistance and series resistance cannot be reached the optimum at the same time, and there must be a trade-off for the 2 parameters, and which will limit the cell performance. And what we want is the high resistance, sheet resistance, and low series resistance. And that is the design idea of the upgraded PERC cell. For the 2nd generation PERC cell, the main upgradation are the bifacial generation and the application of selective emitter. As you know, the shallow junction diffusion increases the sheet resistance of cell, and the heavily doped selective emitter could increase the conductivity of the cell and hence reduce the series resistance. Therefore, the laser is used to melt phosphorus silicate glass, and the heavily doped phosphorus is formed in the bottom. With the application for the combination of the selective emitter and the high resistance technology, there is a significantly increase for the open circuit voltage, short circuit current, and fill factor, and the efficiency of the cell has a great improvement. Although the optimized rearranged backsheet grid could provide more electricity on the backside and get some electricity gain for the bifacial module, the mass production cell efficiency now could reach between 23.3% to 23.5%. Moreover, this optimization also increased the performance under the short wavelengths, as you can see from the external quantum efficiency graph. In comparison with the 1st generation PERC technology, the upgraded generation 1 performs better, especially under the low wavelengths from 300 to 500 nanometer lights, as you could see from the result of the EQE. And the performance ratio for the PV farm using upgraded generation technology improved apparently, as you could see that from the graph, 2 to 3% power generation gain is occurred, and from the upgraded PERC cell. And here is another important technology we use to assure the lower degradation of the monocrystalline module. That is the usage of gallium-doped wafer. As you know, that using the boron-doped wafer could produce the boron oxide composite under the sunlight, which will increase the degradation, especially for the first year. And now, using gallium as the doping element of wafers solves the problem and hence reduce the lifetime degradation. The degradation for the first year is about 2% and 0.50% per year for the single glass module from the second year to 25th year, and 0.45% per year linear degradation from the second year to 30th years for the double glass module. Another important technology we had to mention is the multi-busbar technology and round ribbon. Firstly, I will talk about the advantage of using 11 busbar pattern. It could reduce the transmittance distance of currents, which makes the collection of current easier. The round ribbon increases the cross-section area of ribbons and could reduce the resistance. So there are lower resistance loss, and hence there will be more energy yield. Moreover, it will reduce the risk of cell crack and broken fingers on the module because the pressure on the cell is lower. Secondly, it is the round ribbons. The reasons for using round ribbons is to improve the optical utilization. As you could see, that there will be more reflective light between the glass and oblique incidence and solar cell, and hence improve the light trapping. And thinner ribbon could reduce the stress on the cell and improve the reliability. The durability under the temperature and load fluctuation could be better. The test has shown that the power loss after thermocycling and dynamic load could be reduced. And next, I will talk about the half cell technology. Firstly, the half cell could lower the internal resistance loss and improve the photoelectric conservation efficiency. Secondly, it will reduce the module temperature in comparison to the regular module. As you could see from the graph, the nominal operating cell temperature could be 2 to 3 degrees Celsius lower in relative to the full cell module. Moreover, the split junction box design could optimize the circuit and reduce the current mismatch for the mismatch loss for the module. Consequently, the temperature of the module could be 10 to 20 degrees Celsius lower than the full cell modules under the hotspot situation. Furthermore, the mechanical load capacity could be increased, and there will be less impact for the shading as well. And here is a summary of the technical parameters of our DeepBlue 3 product. The temperature coefficient is about minus 0.35% per degree Celsius, and there would be a 98.5 efficiency for low light performance. The standardized module size and improved warranty degradation has been mentioned previously. The weight of our single glass module is about 28.6 kilogram for the single module and 31.6 kilogram for the dual glass module. And now I will have a brief introduction of the DeepBlue 3 Pro, which is the upgraded version of DeepBlue 3. It uses a gapless flexible interconnection technology developed by JA Solar, and it will increase the power, the module efficiency about 0.4% and increase the power output about 10 watts. Moreover, it will also increase the bearing capacity of the cell and the module. And hence, it could bear more severe reliability tests to ensure the reliability of the product. And finally, I will talk about the value analysis of our product. A third-party EPC company ever calculated the cost evaluation using the fixed structure rack. It shows that the system cost will be the lowest using the 18278 module, and the system cost of 18272 module and 21060 module are almost the same. However, the data is just for a specific project evaluated by the third party and could just be taken as a reference. More case-by-case study has to be undertaken. And there is also another evaluation from the top 3 single-axis tracker manufacturer for the cost of analysis of tracker. The evaluation takes 16672 module as a baseline, and it shows that 18278 module could save up to 14% on the tracker. That means the 182 module should be more suitable for the single tracker system. Moreover, there's an evaluation of a 100 megawatt project in Dubai, showing that the result could be showing the result that the LCOE could reduce about 5 to 7%, as you could see, including rack usage, inverter, the reduction of rack usage, inverter cost, land saving, etc. And from the above simulation, it could be seen that 18278 module has a better lifetime accumulated power output in comparison to larger module. Although there are some decrease from the cable loss, cable cost, and electrical system equipment cost, the power output gain from the 182 module bringing lower levelized cost of energy and benefits for the end user. It could be just as a reference because it is the evaluation from the third party. So further analysis should be undertaken for different projects. And that's all for my presentation. And thank you.
Thanks, Kuan Chen, for this overview on your DeepBlue products. Maybe a few questions. So, as you said and you pointed out, as an integrated manufacturer, it made sense for you to stay with 182. You could also use your former equipment. You had the experience. But how you see that originally JA came also from wafer manufacturing. You have a strong background and a big expertise in wafer manufacturing. So how are you seeing the future in terms of wafer sizes for module products? So will you stay forever at 182, or will you also go larger? And is 210 maybe even not the end?
I think it depends. Because the main goal for us is to let our customer get benefits from our product. In nowadays, it could be the best using the 182 millimeter wafer for our evaluation, just for our evaluation, I mean. However, if we find a better solution, the wafer size may be still enlarged and it will be more challenging because it is a complex work for the assessment of many aspects, including the logistics, reliability, and the feasibility of the whole supply chain. Is a big system. If there is further information about the larger wafer product, it will be published officially, actually. So what I could tell is that our investigation and research for the module optimization have been going on and without stop. That's it. Thank you.
Okay, and maybe another question is regarding cell technology. We've also heard in other presentations that companies are looking, and Schraban also showed that PERC is now coming somewhat towards an end of the optimization potential. So can you reveal on what JA is working on regarding next cell technologies? Are you working on HAT or on TOPCon or on both? So what's your strategy here?
For us, the other technology could be the N-type passivated contact cell module and HAT module. The next step to increase the cell efficiency could be the N-type passivated contact cell, which is also called Percium DeepBlue, the DeepBlue 4 product, which will be officially published in the future. The production of which is based on the upgradation of the existing production line. The DeepBlue 4 product will also have a higher efficiency and lower degradation, as well as good performance at high temperature and better bifaciality coefficient. And if there is further information, it will be shown publicly. For the HAT technology, maybe it could be introduced in the next few years. It has a lot of advantage for the HAT, as you know, but the big problem is we have to invest in new lines for the HAT production. It is a huge amount of money, and so it will take more time for the mass production of this product. There is a pilot line for the HAT in our research and development center, but nowadays, no further information about the mass production. That's it. Thank you.
Okay, thanks. So I think we have to catch up a little bit on time. I think there is a couple of questions in the chat. It would be great if you could answer them in the chat in written form. That would be nice.
Okay.
Okay, then, yeah. Okay, then once again, thank you. And we continue. So we're moving now from the 182 camp to the 210mm module camp. And the next presentation will be given